Hi friends, my name is Amita and in this video I am going to discuss about a very important topic of in power electronics, that is a single phase half wave fully controlled rectifier. I know that you are aware about the rectifier. It is a kind of power electronics converter which is used to convert a AC supply into a DC supply. As we know that there are two kinds of AC supplies are available. One is a single phase AC supply and another is a three phase AC supply. A rectifier which converts a single phase AC supply into a DC output will be called as a single phase rectifier, whereas a rectifier which converts a three phase AC supply into a DC output will be called as a three phase rectifier. When we talk about a half wave fully controlled rectifier, it means that the rectifier is only able to convert the half of a AC input cycle, that is a positive cycle. Whereas when we say that it is a controlled rectifier, that means the circuit is consisting of an fully controllable devices. That means we are having the full control in the positive cycle also. In this video, I am going to discuss about the operation of a single phase half wave fully controlled rectifier for a resistive inductive load. If you are interested to understand the operation for a resistive load, then you can go for my YouTube video where I have discussed about the operation for a resistive load. The description link for that YouTube is given below this video. So now without wasting time, I am directly switching to my screen where I will explain the power circuit diagram followed by the operation for a resistive inductive load and the appropriate waveforms. So my dear friends, I am sharing my screen. So let us discuss about single phase half wave fully controlled rectifier. So very important point about it, it is used to convert the single phase AC supply into DC supply. Now, if I talk about its power circuit diagram, it is consisting of a fully controlled device, that is SCR, which is also called as a thyristor. There is a AC voltage Vm sin omega t, and here the type of load will be an resistive inductive load RL. As in this video, I am going to tell about the operation of a single phase half wave fully controlled rectifier for a resistive inductive load. T1 is nothing but it is a silicon controlled rectifier. It is a fully controllable device that is also called as an thyristor. R and a load L, it is a resistive inductive load. Resistive inductive load. Okay, and Vs is the AC input voltage. So this is something about the power circuit diagram. Now let us try to understand its operation. So operation, please mind it, I am explaining the operation when the load is resistive inductive. I already told you that the operation of this rectifier for a different type of load will be different, because in the basics of electrical engineering we have already gone through that when the load is resistive, the voltage and current will always be in same phase. When the load is resistive inductive, then due to the inductive feature, the current lags from the voltage, and when the load is resistive inductive and E, then the output will be different. So this video I am mainly focusing on the operation of an half wave rectifier for a resistive inductive load. Now before understanding its operation, I just want to tell you that we will discuss its complete operation for a both cycle of a AC input. You know that the AC supply is represented like this. This is omega t, this is Vs, supply voltage waveform. The peak value is Vm and this is 0, pi, 2 pi, 3 pi. So you can see that the time period of this time period of this AC cycle. What is time period? Time period is nothing but it is the time after which the cycle repeats its value. So time period for this is 2 pi. Okay, and you can see 0 to pi it is having positive magnitude and pi to 2 pi it is having negative magnitude. So positive cycle of a AC input, positive cycle of AC input exists between 0 to pi and negative cycle of AC input exists between pi to 2 pi. So that means when that kind of input is connected to a SCR, then during positive cycle the SCR will be forward bias and during negative cycle the SCR will be reverse bias. So to understand its complete operation, we will be able to understand it with two cycles. One is I will understand its operation during positive half cycle of AC input. So how the circuit will operate? It exists between 0 to pi. Now, when we have gone through with the basic concept of a silicon control rectifier, that time we understood that during positive cycle, SCR will be forward bias at 0 itself, but it will not start conducting at 0 because to make the SCR conducting, it is not sufficient to make it forward bias, but the second condition should also be fulfilled, that the anode cathode current should reach to the level of latching current, and this can be achieved only by connecting the gate supply, because when the SCR is forward bias, the middle junction of a SCR is reverse bias, and to break down that junction we have to connect the gate supply. So that means the conduction of an SCR to not only it will depend on the forward bias, but at the same time it will also depend on that when the gate pulse is given to it. So suppose the gate supply is connected at firing angle alpha. What is firing angle? Firing angle is nothing but it is the angle between the instant at which the device is forward biased to the instant at which the gate pulse is given to it. So that means during positive half cycle, to understand the operation of a rectifier, we have to split into two parts. One is during 0 to alpha and the second one is during alpha to pi. So 0 to alpha, as you know that the SCR is forward bias at 0, but it will not start conducting as the gate pulse is not given to it. So between 0 to alpha, SCR will be open circuit and the upper terminal of the supply is positive as it is a positive supply. So Vm sin omega t, and the load is resistive inductive. So under the condition, the voltage across the load will be output voltage, and you can see as the SCR is open circuit, so the supply voltage is not connected to the load, so the output voltage will be 0. Now when I talk about alpha to pi, as we have given the gate pulse at alpha and it was already forward bias at 0, so T1 will be acting as a short circuit. So RL, and here I have given the input voltage Vs is equal to Vm sin omega t. So under that condition, the output voltage V0 will be equal to Vs, because through this T1 short circuit, now the supply voltage is fully connected to the load. So output voltage will be Vs. So between alpha to 0, output voltage is 0. Between alpha to pi, output voltage will be equal to the supply voltage. Whatever the instantaneous value of a supply voltage will be there, at that time the output voltage will be equal to that value. Now this is something about the positive cycle. Now let us discuss what will happen in the negative cycle. So how the circuit will operate during negative cycle. So B part, operation during negative half cycle of input of AC input. and this will exist between pi to 2 pi. Here, before going into detail of the operation of a negative half cycle, I just want to tell you that as simply making the SCR forward bias doesn't guarantee to make it on, similarly, simply making the SCR reverse bias doesn't guarantee to make it off, because to make the SCR on, as the two minimum conditions should be fulfilled. One condition, it has to be forward bias, and the second condition, the anode cathode current should reach to the level of latching current, and this latching current we can achieve by connecting the gate supply. Similarly, to make the already conducting SCR off, minimum two conditions should be fulfilled. One is it has to be reverse bias, and second one, anode cathode current flowing through the SCR should reach to the level of holding current, and that holding current for all theoretical purpose we assume 0. Now since here the type of connected load is inductive, and in case of inductance always the current lags from the voltage, that means when the voltage is 0 at pi, the current cannot be 0 at pi, it will be 0 after pi, somewhere at beta. So that means the SCR will not be off at pi, but it will be off at beta when both conditions of making SCR off will be fulfilled. Okay, that beta is called as an extinction angle. So we will write due to inductive load as current lags from voltage, hence the current will be 0 after pi, somewhere at beta. Beta is extinction मतलब जहां पर करंट खत्म होती है, somewhere at extinction angle beta. Okay, so that means during negative half cycle we will try to understand its operation, one part between pi to beta. Okay, so pi to beta, how the circuit behaves, the thyristor T1 is still conducting after pi also, because the SCR is reverse bias, but as the current through SCR is not 0, so it will still conducting due to the inductive load, and the lower plate of a supply is now positive because the negative supply is there. So although the SCR is reverse bias, but as the current is not 0, so SCR will remain conducting, and the output voltage will be equal to Vs between pi to beta, because jab tak till the SCR is conducting, always the output voltage will be equal to the supply voltage. And here in the case of resistive inductive load, the SCR is conducting after pi also up to beta, because the current is not 0 at pi. Now as at beta the current is 0, that means both the conditions to make the SCR off now fulfilled at beta. So second part of negative cycle between beta to 2 pi. So beta to 2 pi mein now the SCR will be off, as both the conditions of making SCR off are now fulfilled, and Vs is equal to Vm sin omega t will be the input voltage. SCR is off and this is load. Now again the load is disconnected from the supply, so the output voltage is now 0. So you have seen that during positive cycle output voltage between 0 to alpha is 0, alpha to pi it is Vs, pi to beta it is Vs, and beta to 2 pi it is again 0. So now at last I am going to make the waveforms for you. So if I want to plot these waveforms followed by the analysis, so let me draw the waveforms. This is omega t, this is again omega t. Here I am going to plot Vs, this is Vg, this is load voltage, this is omega t, this is load current, okay, this is Is also, and this is It1 also, okay, and here Vt. So let me draw with a yellow color. The AC voltage is like this. This is the input voltage. This is 0, this is pi, this is 2 pi, this is 3 pi. And we have given the gate pulse at alpha. So this is alpha and this is alpha. Now let me extend these instants. This is alpha plus 2 pi. Okay. Now you know that the SCR will be on at alpha. So after alpha, whatever the instantaneous value will be there, that I am going to get up to pi. So alpha to pi, I am going to get the output voltage. As you know that in case of inductive load, the current will not be zero as the voltage is zero, because current lags from the voltage. What is the meaning of lag? Lag matlab if the current is lagging from voltage, that means it will reach to its minimum and maximum value after the voltage. So that means if the voltage maximum value at this point, the current will reach to its maximum value delayed by this, and somewhere at beta it will be zero. So this is load current. So let me extend this beta also. So that means SCR is conducting up to beta. That means after pi also, whatever the input voltage will be there, that I am going to get the output voltage. Now at pi the SCR is off. So from pi to 2 pi plus alpha, the load voltage will be 0. So this kind of output voltage I am going to get, and this here, this angle will be beta. That means SCR will conduct from alpha to beta. So in this case, SCR will conduct from alpha to beta. Okay, so this is the load current. Now if I am going to plot the voltage across SCR, since alpha to beta the SCR is conducting, so alpha to beta I am going to get the zero output voltage, zero voltage across the SCR, and for rest of the duration, whatever the supply voltage waveform remains left, that will be the voltage across SCR. So this will be the voltage across T1. Okay. So and this is because of the conduction T1. So these are the waveforms related to a single phase half wave fully controlled rectifier for a resistive inductive load. Now if you see the output voltage time period is 2 pi. So time period, output voltage time period, output voltage waveform, if you see it, the time period for that will be 2 pi. And you can see alpha to beta, I am getting the sinusoidal function. 0 to alpha function is 0 and beta to 2 pi function is 0. So if I want to see the analysis part of this, if we want to do the analysis, so my interest for the analysis, my interest is to calculate VDC, or you can say V naught, means average value of DC output voltage. This I am interested to calculate. I am interested to calculate IDC or I0, that is called average value of DC output current. And similarly, I am interested to calculate VRMS. That means VRMS matlab RMS value of, that means we are interested to calculate the RMS value of DC output voltage. Why we are going to calculate the RMS value of DC output voltage? Because the kind of output which I am getting with the help of rectifier, that is not a pure DC, it is not a constant DC, it is a pulsating DC. So that's why we are calculating the RMS voltage also. And similarly, IRMS, that is RMS value of DC output current. In this video, I am going to simply tell you how to calculate VDC and VRMS just because of the time constraint. So if you want to calculate the VDC, that is equal to V0, you know that can be calculated by 1 by time period integration 0 to t f of t dt. Okay, so what is time period? 1 upon 2 pi, 0 to 2 pi, f of t dt. Now you know the function throughout the time period is not fixed. So 1 upon 2 pi, we have to break the integration limit. 0 to alpha function is 0 d omega t. Alpha to beta function is Vm sin omega t d omega t. And beta to 2 pi function is again 0 d omega t. So this is how we are going to calculate average value. Now it is equal to 1 upon 2 pi. This whole term will be 0. So only this term will come and this is also 0. So alpha to beta Vm sin omega t d omega t. This is how we are going to calculate. So 1 upon 2 pi. I can take Vm out. So what is the integration of sin omega t? Minus cos omega t. Okay. And limits from alpha to beta. So if you solve it, what I am going to get, VDC, or it is equal to V naught, that is equal to Vm upon 2 pi minus cos omega t, limits from alpha to beta. Now put the limits, Vm upon 2 pi minus cos of beta, and 1 minus this, 1 minus of lower limit, so cos of alpha. Now I can rewrite like this, Vm upon 2 pi cos of alpha minus cos of beta. This is the value of VDC, or it is equal to V naught. So this is how we will calculate. ये क्या है? Average value of DC output voltage. Okay? So this is how we are going to calculate the average value of DC output voltage. The next thing which I am going to calculate, that is VRMS value of DC output voltage. Okay, so how to calculate VRMS? VRMS is equal to under root 1 by time period integration 0 to t f square t dt. This is the formula. Now what is time period? Time period is 2 pi. So under root 1 upon 2 pi integration 0 to 2 pi f square t dt. Now since you know the function is not same throughout the time, so how we can write under root, we have to break the integration limit as the value of function is not constant throughout the time. So 0 to alpha function is 0 d omega t. Alpha to beta function is Vm square sin square omega t d omega t. And beta to 2 pi function is again 0 d omega t. So if I solve it, what I am going to get, VRMS, that is equal to 1 upon 2 pi, under root से बाहर ले लिया, then root alpha to beta Vm square sin square omega t d omega t. So 1 upon root 2 pi. Now under root Vm को square को under root से बाहर लिया तो Vm. Now sin square omega t को I can write 1 minus cos 2 omega t by 2 d omega t. If I do the integration of that, Vm upon 2 pi under root integration of 1 by 2 omega t minus sin 2 omega t, cos 2 omega t का integration is this, limits from alpha to beta. Now I have to open it. What I will get, VRMS is equal to 1 by root 2 pi integration, under root 1 by 2, upper limit is beta, so 1 by 2 beta minus 1 by 2 lower limit alpha. Okay, then minus sin beta by 4 and 1 minus of this and 1 minus of lower limit. So plus sin alpha by 4. So this much I am going to get. If I further solve it, root 2 को मैं 2 को under root से बाहर लूंगी तो it will be 2 root pi, and this I can write it as beta minus alpha, then minus 1 by 4 sin beta minus sin alpha. So this is the RMS value of a DC output voltage. So now I am stop sharing my screen. My dear friends, whatever information I have shared in this video related to the operation of a single phase half wave fully controlled rectifier for a resistive inductive load is now clear to you. If you are interested to learn the operation for single phase half wave fully controlled rectifier with RLE load, then keep watching my video. Thank you. Goodbye.